For the past few years, our interaction with large language models has followed a strict one-way path. You input a natural language prompt, the model processes it, and it outputs a static, rigid block of code. This zero-shot generation works for writing a quick script or a standalone function. But when applied to long-horizon, complex workflows, like debugging a million-line enterprise repository or controlling an embodied robot, the stateless approach lacks the necessary durability. The failure happens because the system relies entirely on internal latent reasoning. In multi-step tasks, a model must hold intermediate logic, feedback, and variables inside its finite context window. Eventually, that window fills up, logic degrades, and the model loses its objective. Scaling up parameter counts and training larger models does not eliminate this specific reliability bottleneck. The issue is architectural, not a lack of computational horsepower. To fix this, researchers are inverting the relationship between the model and its output. Instead of treating code as the final artifact the system produces, code is being reframed as the operational substrate of the system itself. Achieving actual autonomy requires stepping away from isolated text generation and building an infrastructural framework around the model. We call this the agent harness. An agent harness is the software layer that wraps the language model. It mediates every interaction the model has with external tools, memory databases, and the target environment. In this framework, code serves three critical properties. First, code is executable. When a model proposes a solution, the harness runs it. This provides deterministic feedback and formal verification, replacing vague assumptions with hard pass or fail metrics. Second, code is inspectable. Rather than hiding intermediate computation inside a black box of neural weights, the model externalizes its logic into structured, readable syntax that the harness can trace and evaluate. Third, code is stateful. It allows the system to preserve its interaction history, edit variables, and maintain progress across hundreds of sequential steps without starting over from scratch. This diagram outlines the code as agent harness taxonomy proposed by researchers. It organizes the system into three distinct architectural layers: the interface layer, mapping reasoning to action, the mechanisms layer, dictating planning and memory, and the scaling layer, coordinating multiple agents. Organizing the harness around these layers provides the structural groundwork necessary for a model to handle complex, multi-stage tasks over time. The interface layer is the boundary where the model meets the real world. Its entire function is converting the model's abstract intent into grounded, testable structures. The standard chain of thought method uses text, which is prone to logic errors. The interface layer instead uses program of thoughts, writing logic as a script and passing it through a compiler. Delegating calculation ensures mathematically sound results. This same principle applies to taking action. In an agentic system, code serves as the exact policy interface between the brain and the body. If the model's intent is to fix a repository bug or command a robotic arm to grasp an object, it doesn't output vague text. It maps that intent to constrained, executable skill libraries via direct API calls. The environment itself is also translated into code. Instead of feeding the model a text description of its surroundings, the interface layer feeds it ground truth data structures. A software bug is represented by execution traces and unit test logs. A web browser is represented by a queryable document object model tree. At every step in the interface layer, natural language ambiguity is stripped away. The agent is forced to prove its reasoning and ground its actions in executable reality. Once the model's outputs are strictly executable, code generation becomes a continuous interaction of writing, testing, and debugging that requires rigorous system-level control. The baseline mechanism for controlling this loop is linear decomposition. The model writes a flat, step-by-step numbered list of instructions in natural language and then generates code step by step. This works for simple scripts, but fails in complex software engineering. If step 2 of a linear plan breaks a dependency required for step 5, the model won't realize it until the end of the run, resulting in a cascade of failures. To manage dependencies, the harness relies on structure-grounded planning. The plan is matched directly onto the repository's file structure. Before writing a line, the agent understands which files interact, constraining its action space to avoid overwriting critical functions. The most advanced systems take this further with search-based planning. The harness allows the agent to explore multiple trajectory branches simultaneously, testing different implementations and pruning the failures based on live test feedback. Effective planning in an autonomous system isn't about writing a better prompt. It is about engineering a verifiable search and control loop that can adapt to failure. Even with perfect planning, long-horizon tasks hit a hard physical limit. Searching repositories, running tests, and reading execution logs generates a massive amount of text. If you feed all of that raw state back into the model, the context window overflows. Through context compaction, large files are compressed into lean summary notes and offloaded to an external database, creating semantic memory. The agent then queries this database, pulling only the relevant structural snippet into its current context. This leaves the model's working memory open. Working memory is strictly budgeted to hold only the tools needed for the immediate next action, like active variables, current localization clues, and recent failed test logs. Finally, the harness utilizes experiential memory. When the agent successfully completes a complex task, the harness saves the fully validated trajectory, the reasoning trace, and the accepted code. When the agent encounters a similar problem later, it retrieves this stored experience. It instantly knows the correct architectural pattern to use, bypassing the need to blindly search and reason from scratch. By separating memory into distinct, queryable layers, the harness prevents catastrophic forgetting and maintains long-term consistency without crashing the model's compute limits. The next frontier in this architecture scales outward. We move from single, isolated agents to multi-agent ecosystems, where models take on specialized, parallel roles. One acts as the coder, another as the reviewer, another as the tester. But coordinating these roles introduces a severe communication bottleneck. Passing massive textual summaries back and forth between different language models is inefficient, slow, and prone to data loss. The harness solves this by removing latent text exchanges entirely. These specialized agents do not chat with one another in natural language to track their progress. The code harness is the shared communication substrate. Agents operate around a central repository via pull requests and unit tests. A coder pushing a change triggers the reviewer to run its test script, returning a pass or fail signal. Everyone maintains perfect state synchronization. Code artifacts and execution logs act as the universal language. They provide a precise record that allows complex multi-agent systems to coordinate reliably. As the underlying reasoning capabilities of language models mature, the primary engineering challenge shifts toward the design of the harness itself. Natural language is an excellent tool for understanding human intent, but a difficult medium for executing it. Code bridges that gap because it is executable, inspectable, and stateful. By moving past isolated text generation and mastering the agent harness framework, the industry can transition from building simple chatbots to deploying reliable, long-horizon digital workers.